So here's a quote from Bill Watterson. He was a cartoonist. Well, he still is a cartoonist. He's still alive. And he said, "I find my life is a lot easier the lower I keep my expectations." This is a humorous statement, but I do think that there's a kernel of truth in it. Most humorous things have a kernel of truth. And I think it's important to be realistic and say, look, I'm not going to have infinite time, I should plan accordingly. One of my biggest challenges I have personally, and this is my own struggles, it may or may not apply to you, is I always think, I expect myself to have lots of time in the future, and I overcommit. Be realistic. Plan realistically, and then life will work out a lot better. Now, our goals for today, we're going to try to do two things. I hope we make it through. We're going to talk about Bayes' formula, and what's the goal of Bayes' formula? We talked about conditional probability last time, probability of A given that B is true. But what if we want to switch the tables and say, well, what if I want to know probability of B given A is true? Can we do that? Well, yes, but you have to be careful. The probability of A given B is not the same as probability of B given A, but Bayes' formula says here's how you do it. And it looks complicated, but we'll talk about where it comes from in a few minutes. And the good news is, I like the advice in the book. Don't try to memorize it necessarily. Learn how to use processes to get the answer. The other thing we're going to talk about is the expected value of a random variable. And you can think of this as sort of, what's the average outcome of my experiment that I'm about to conduct? I roll a dice. What's the average of all my possible outcomes? That's the kind of question that expected value can answer. So, Bayes' formula, we're not going to go too crazy. It basically falls from a few ideas. We talked about last time that the probability of A intersect B is the probability of A times the probability of B given A, but it's also the probability of B times the probability of A given B. You'll notice we have our two conditional probabilities here, just we've swapped the order. So what we can do is we can solve for the probability of B given A, and lo and behold, we get this basic fact, probability of A given B times probability of B over probability of A. And that's basically it. That's the idea. Now, one thing you can do is you can go a little bit further and say, what's the term downstairs? It's the probability of A, and you can break that up into pieces. So for example, you can say, look, my universe has either you're B or you're not B. So you can split up the probability of A into two parts. How much of A is in B, how much of A is not in B. And so that's what's going on here. Now, as I mentioned, in practice, you can oftentimes figure this out using a probability tree and understanding how things connect. So you don't have to memorize the formula. You have to be able to derive the answers. And there's other ways to get to the answers. And I should say, this is not my way of saying, this is not an important formula. This is a very important formula, an incredibly important formula. A lot of industries run on this formula. The insurance industry, for example, medical industry, they need this. But there's other ways to get the answers. All right, so let's see if we can try this out. Use Bayes' formula to find the probability of U1 given W. Now, we don't know what U1, U2 means. We don't know what B and W means. But that's okay. We have the probability tree. So, what do we have? Well, we know we're in the universe where W happens. Because we're told probability of U1 given that W is true. So what we'd like to do is say, well, let's look at everything where W actually happens. And we can find that by looking at our tree and saying, where's W? Well, here and here. Those are the two locations W shows up in our tree, our two leaves. Now, I would do the following. I would take the product going down. So 1/3, 2/5 says this possibility of ending up down at the bottom in our probability tree would be 2/15. On the other hand, if we take the other path down, 2/3, 3/4, then 2/3 times 3/4 is 2/4, or we can just say 1/2. So that's our space. Now, we want to have U1. We say, okay, now that we want to have U1, we look for where does U1 show up, and it shows up earlier up in the tree. This is sort of the point here. See, we know the probability of W given U1 is just this 2/5. We're swapping it around. So what do you do? Well, we go from here down to any of the branches that we said matter. So that's the 2/15. So what's the answer? Well, it's the probability of A given B times probability of B. So this 2/15 here, that's this top expression. That 2/15 is this part. Divide by, then we have the 2/15 plus the 1/2. So this is the same piece that's upstairs, and then this is essentially the complement. The complement of U1 is U2. And that's our answer, but of course, this isn't a very pretty expression. So we can clean it up. Here I'll multiply by 30/30. Now, why 30? I want to get rid of fractions as much as I can. And I'm looking in the fractions that are showing up in this expression. There's 15 and there's 2 in the denominators. I say, well, if I multiply everything by 30, no more denominators. So for instance, upstairs, what will happen? Well, we'll get 15 goes into 30, remains 2. 2 times 2 gives us 4. And again, 15 goes into 30, gives us 2 times 2 makes 4. 1/2 times 30, that's 15. So we end up with an answer of 4/19. All right, so that's the idea. Any questions on where the pieces came from? So the denominator here, that's just look for, you have this condition on W, look for where anything that has a W ends up downstairs. Add all those up. And then you say, okay, U1, look for everything that has a U1, and then go down and see where it hits a W term. Well, don't worry, we'll get to do it again. We'll get good at it, right? Yeah, of course. Of course. All right, well, a lot of words on this one will be, this will be an essay problem. A new test is being developed to detect tuberculosis. Now, what's going to happen? Well, is it a good test or not? By testing on a small number of people, the following was determined empirically. 8% of the people have tuberculosis. That's the first item. 96% of the people with tuberculosis tested positive. 2% of the people without tuberculosis tested positive. I don't know why I have the word "is" there. I shouldn't be there. We'll just... Now the question. What is the probability a person has the disease if they tested positive? All right. Now, what is this asking for? Well, we're trying to understand, how good is this test? If I get this test back and it says, oh, you tested positive, How worried should I be? That's what we want to know. Now you might say, 96%, that's pretty good. That's how many people who have tuberculosis test positive. And on the other hand, if you don't have it, 98% of the time it says, hey, you don't have it. So 96%, 98%? If you heard these numbers initially, how do you feel about this test? You're like, wow, 96% or 98% of the time, it gives the right answer. And now it tells you you have tuberculosis. How worried should we be? Well, let's draw the tree. Now, there's two things that are happening. You have tuberculosis or you don't have tuberculosis. And the other thing that's happening, you test positive, you test negative. So you kind of have to make a decision, like, how do we arrange our tree? And here, there's kind of a clue. The clue is coming into this information, these last two bullet points. 96% of the people with tuberculosis tested positive. Now, what does that say? The with tuberculosis, this is a conditional statement. So it's saying, if you have tuberculosis, then I can tell you how the probability that you test positive. And again, this without tuberculosis, this is a conditional statement. So once you have conditional statements, you say, if it's conditional on something, that thing should come first. So when we make our tree, we can say, let's start. And now we have two possibilities. We'll do shorthand. Tuberculosis will be T. And is T prime okay for not tuberculosis, or should we come up with like a more fancy way to say this? So T prime, this prime, remember, means complement. So it's like not that. Okay, now this is a probability tree. So that means that there needs to be probabilities attached to the edges. What's the probability that you have tuberculosis? Do we know that? Probability that we have tuberculosis, is that given to us? What is it? It's the 8%. So here, this is 0.08. Well, then the not needs to be 1 minus that, so 0.92. Okay, so we've made it through one level. Now, we keep going. We have, you test positive, you test negative. You test positive, you test negative. Those are other two events. So, that's where these other two statements come in. 96% of the people with tuberculosis tested positive. So what's the value for this edge? T to plus. 0.96. Which means this is 0.04. 2% of the people without tuberculosis tested positive. Okay, so without tuberculosis, that's the complement T prime, tests positive. So that is 0.02. And then that means that over here, you get 0.98. Okay. Well, now we have the first question. What is the probability a person has the disease, excuse me, if they tested positive? So what we're after is the probability of T given positive. You can think of it as here, this 96%, this is the probability of being positive given t. And here, this is the probability of positive given t complement. So we're switching the conditional statements, how they relate to each other. Okay, well, we do a similar thing. We say, well, now we're in the universe of testing positive. So we look to where we test positive. We're in those two places. And at these two places, we're going to have numbers like 0.96 times 0.08, 0.92 times 0.02. So, what's our answer? Well, it's going to be a fraction. We're in the positive universe, so we're going to add up all the places where we end up with the positive. 0.96, 0.08, plus 0.92, 0.02. Upstairs, what do you put? We want to have the part where we're positive and we were in the tuberculosis. So we're looking for everything that comes down from the tuberculosis condition. So upstairs we have 0.96 times 0.08. All right. Good. Now, that's not a number I can compute in my head, but that's okay. That's why we have things that can do that computation for us. Ah, life is wonderful. Okay, we enter those numbers in, we hit equals, and this tells us that we are 0.8067 ... or about 80%, maybe 81%. Okay, so then there's a question. What is the probability a person does not have the disease if they tested positive? So how do you find that? Well, how do these two relate? Because in both cases you tested positive, so either you have it or you don't. So what's going to be true is these need to add up to 1. So our conclusion is it's about 20%. So even if test says you have it, you're like, oh, this test is like 96%, 98% accurate. You still have a 20% chance that you actually don't have this disease. Now you might say, wait, well, hold on. How did it go from like this high accuracy to being like, whoa, there's like 20% I don't have it? And essentially what's happening is because it's so obscure, relatively speaking, and I will say there's a lot of diseases that are much more obscure than 8% of the population. There are so many false positives that it causes it to be a little bit less effective. So there's accuracy and there's efficacy. So that's why they say, get a second opinion. All right. Any questions? Okay. Let's do one more. Now, you might say, what? Not a lot of words here. We're given a probability tree. It's on here, the left-hand side. We want to fill in a probability tree. And as you look at it, you say, well, what's different? Well, what's different is we first say, let's look at A, and then let's look at B. So what's happening is essentially this part right here, this is having B is conditional on A. Because first you say what happens to A, and then once you know whether A is true or not, then you say what's happening with B. On the other hand, if you look at the other tree, what happens? Well, we first look at B, and then we look at A. So here, it's A is conditional on B. So we're swapping the order. And this is the idea of Bayes' theorem. We're swapping how these things relate one to another. All right, so that gives us a pretty good idea of where we can start. And I like to fill in the probabilities downstairs. So 1/4 times 1/5, that's 1 over 20. 1/4 times 4/5, that becomes 1/5. 3/4 times 3/5, that's 9 over 20. And 3/4 times 2/5 is 6 over 20. Maybe I should write 1/5 as 4 over 20, just so that they all look the same in terms of being over 20. Okay, so we begin. And don't worry, it won't take us so long. Let's start with the edges up here. And I want to say, look, I'm at the start. What's the probability of B? What can I do? We come to this tree. Where do we look? We look for the B's. Yes? So, if we add these up, 1/20 plus 9/20, what does that give us? 10/20 or a half. Now, once we know this, we can say, look, something has to happen at the start. So, what's this edge? Also a half, because it's 1 minus a half. All right, now there's a couple different ways that we can go from here, but I would just say, let's suppose I wanted to find this edge, this probability of A given B. Well, one thing we can do is you can say, well, I can go down here and say, in this branch, both B and A needed to be true. Over here, both B and A being true gave us a 1/20. So that says this also needs to be a 1/20. So if I know I have a probability of a half, I have this probability, which I'm trying to figure out, and then if I multiply them together, I get 1 over 20. That should be enough to figure out what this should be. So what half times what gives 1 over 20? 1 over 10. And we can do that for all these situations. So if I want to know what is B given A complement, well, I look for where is B and A complement showing up over here. That should be a 9 over 20. B complement in A, well, that's B complement in A is over here, and that's a 4 over 20. And here, B complement A complement, I see a B complement A complement, that's 6 over 20. So that the probabilities that the leaves are shuffling around. And now, since we already figured out the probabilities upstairs, well, a half times something gives 9/20, so that's 9/10. We could have, of course, said 1 subtract a tenth is 9/10. A half times something gives us 4/20. And, well, okay, so what does that? And I should have said here, 4/20 is the same as 1/5. So a half times something gives us 1/5. All right, 1/2 times something equals 1/5. What's our something? Multiply by 2. 2/5. So we get 2/5, 1 subtract 2/5, 3/5. And there we go. All right. So the moral of the story, if you understand probability trees, you can answer the questions that you get asked that relate to Bayes' theorem. And so, know your probability trees. And I think that's good advice. All right. So, we're going to switch gears now into the second half of today, because that's right, 2 big ideas today. So, the second half of today is we're going to build up to the idea of expected value. And to understand what's happening is we're going to talk about events. We've been talking about probabilities, but oftentimes they connect to things which have counts or numerical values. So again, it comes back, it's like you roll a dice, and a die has some numbers, 1, 2, 3, 4, 5, 6. And so the outcomes are numbers. So when the outcomes of your event have numbers attached, then we call that event a random variable. The idea of randomness is not so surprising. We're talking about probability. And the idea of variable is just it's something which can change, but it will be a number. Now we use capital X to denote the random variable. We use a little x to say, this is a possible outcome of our random variable. So if I was, for example, going back to the dice, we say, well, the dice is a capital X. Little x would be the numbers 1 through 6. And then we have the probability of x, and that's the probability of x occurring. So it's how likely is that to be as an outcome of your event. And you could also write this as what's the probability that the random variable produces x. Okay, so what's the expected value? Well, the name is very descriptive. It's what you expect. But a better way to say it's your average. It's the average value that you would get. Now, of course, in any single event, you won't ever get the average. Well, you might get it in some cases. But what tends to happen when we talk about the average is, imagine doing it thousands or hundreds of thousands of times, over and over and over again. And then you say, look at all of those and average out those numbers, because our outcomes are numbers. And that's our expected value, what we would expect on average if we do it many times. Now, how do we compute it? Well, we don't want to do it 1,000 times. But that's okay, we don't need to. Here's what you do. Suppose here are our possible outcomes, x1 through xn. Now, what do we know? Well, we know if we sum the probabilities, they better add up to 1, because that says something has to happen. We can't have the case where nothing happens. Something has to happen. And then you say, okay, take x1 times the probability of x1, and x2 times the probability of x2, all the way to the end, xn times the probability of xn. Add all those up, and that is your expected value. So that's the computation. All right. Let's try this out. So, here we go. You decide to make a bet with a friend. Now, the math department does not condone gambling, but for the purposes of the expected value, imagine that this does happen. And you're going to roll a fair 6-sided die. So each of the numbers 1 through 6 will occur with equal probability. If the die comes up 1 or 6, your friend pays you $5. If it comes up 2, 3, 4, or 5, then you pay your friend $3. Now, what is the expected amount that you're going to win or lose? In other words, if you play this game, you're either going to get $5 or you're going to lose $3. But what do you expect to happen? Okay. Well, we can think of our X as our dice. But really, we have this game. We can think of our two things, our winning and our losing. Okay, what's the probability that you win? 2 over 6. Also, we can write it as 1 over 3. And the probability that we lose? Well, it's 4 over 6, or 2 over 3. So, what do we get? Well, our expected value of x, well, we get $5 on win. So it's $5 times the probability of winning plus negative $3 times the probability of losing. So that becomes 5 times 1/3 plus negative 3 times 2/3. Or 5/3 minus 6/3, which is negative 1/3. So if we play this game with our friend, we lose negative 1/3 in expected value. Now, of course, that can't happen in one game. But what this means, if you played a long time and you added up your wins and losses and you divided by the number of times you played, you'd be close to negative 1/3. It's the amount you expect to lose. And so this is not a game that's good for you. It's not. It's okay. There's worse games. And this, by the way, is how casinos make money. They say, look, let's play a game. Come join me. We'll play a game with you. And they figure out what's the probability that you'll win and make money, and they'll figure out what's the probability that you'll lose, and the casino will make money. And they make it so the expected value is it's always negative. Now, you don't want it to be too big, because if you lose a lot, you won't play a lot. And if you go to casinos, you oftentimes will see signs saying, this slot machine will pay 96 cents on the dollar. What does that mean? It's saying, hey, here's the expected value. Every time that you play this, you should expect on average to lose 4 cents. They're advertising that you're going to lose money if you do this for a long term. But, in the meantime, they'll reward you with bright flashing lights and very colorful things. And based upon how often I see students looking at cell phones, they like bright flashing lights and colorful things. So maybe it's worth it for that 4 cents. It's up to you. Okay. So, try some more. Here, we'll go. Next problem. Again, this is a bit of a gambling kind of a problem. On 3 rolls of a die, you will lose $10 if a 1 turns up, at least 1 time. Otherwise, you'll gain $8. What's the expected value of this game? So you roll a dice. Now, you don't have to think of it as rolling the same dice 3 times. You can roll 3 dice at once. That's the same thing. But you roll 3 dice and you say, okay, if 1 dice shows up as a 1, I lose. But if they all show up as something else, and there's a lot of other numbers besides 1, I win. Okay, so what do we need to figure out? Yeah, we need to know the probability of winning, and we need to know the probability of losing. Now, the good news is, if we add these up, they have to add up to 1. Now, question. What's easier to compute here? The probability of winning or the probability of losing? Sorry, what? Yeah. So the thing is that having a 1 turn up at least once can get a little subtle, because what could happen? Well, you could have a single 1 turn up, or you could have 2 1s turn up, or they could all be 1. And that gets complicated to keep track of things. On the other hand, if you say, look, no one turns up, then you're like, oh, well, that's more straightforward to compute. So, we want to look at our winning situation. So here, winning, this is no one on any die. What will that turn out to be? So what's the probability that a 1 doesn't show up on a single die? 5, 6. So what's the probability that 1 doesn't show up on any of the die? Having already written down 5, 6, so that's part of the answer. Yeah, you cube it. Using language that we talked about last week, or this week maybe it was this week. Using language we talked about this week, what's the idea about why we cube it? Well, I would say that the word I'm looking for is independence. They're independent of each other. So if I want to know the probability that you don't have a 1 and you don't have a 1 and you don't have a 1, all at the same time. So like we're taking the intersection. We can just multiply the individual probabilities. Now, with that out of the way, what's the probability that we lose? Well, it's 1 minus 5, 6 cubed. All right, because you either win or lose. Okay. Well, you might remember this. We talked about something before of like birthdays. What's the probability if you have so many people in a room that they all have the same birth date? And it turns out to be a little bit surprising. All right. Well, let's see if we can compute these numbers. 5 divided by 6, and then we'll cube it. And so the probability of a win, we'll say it's about 0.579. And then what can we do? We can just take 1 minus that, but all right, well, we'll just start from scratch. 1 minus 5, 6 cubed, that's about 0.421. Okay, so we're not done, but we've done a lot of the hard part. We've got the probabilities we need. Now we turn it into expected value. Okay, so if we win, we gain 8. So the expected value of this game, well, it's 8 times the probability of winning, and minus 10, so plus the negative 10, times the probability of losing. Well, okay, that's 8 times 0.579 minus 10 times 0.421. And I'm not good at some of these computations, so that's okay. 8 times 0.579, good, minus 10 times 0.421 equals 0.422. Woohoo! We like this game. Why do we like it? We make money. The expected value is positive. Money, 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 money. Money. Now, again, please don't go out and start gambling. You have to remember, expected value is one thing, but that happens in the long run. And in the short term, who knows? There is such a thing as, a streak of bad luck, which is to say, randomly, you can lose many times in a row. And there's a famous instance, I think it happened in Monte Carlo, where they had a roulette wheel, and it kept coming up red over and over and over again. And the casino made a fortune because everybody thought, oh, it's come up red so many times. They kept throwing lots of money on black. you can't know what the next thing is going to happen. Random events don't keep track of what came before. So be careful. Be careful. All right. Now, something that's not gambling. Well, maybe it's not. Insurance. And insurance is basically a gamble. You're trying to hedge your bet. You say, okay, what's the likelihood that something bad will happen? All right, so let's take a look at the next question. It says the annual premium for a $5,000 insurance policy against the theft of a painting is $250. Okay, so you pay $250 every year. If nothing gets stolen, then that's it. On the other hand, if you pay $250 and it does get stolen, well, then they'll give you $5,000. Now, it says, if the probability that the painting is stolen during the year is 1%, what is your expected return from the insurance policy if you take the insurance? Okay. Well, what two situations do we have? Yeah, you get robbed or you don't get robbed. Okay, so we already have some information. The probability of a theft, right? It says the probability that the painting is stolen during the year is 1%. All right, that's 1%, 0.01. So the probability of no theft is 0.99. Okay, so what's our expected value? Well, what happens if there's no theft? Let's start there. Let's be optimistic. What do we get? Or what do we lose? We lose our premium. So, if there's no theft, we're out $250 for the year. If there is a theft, what will we have? Will it be 5,000? He says, as though to say, I agree with the idea of 5,000, but there's one more tweak. Because if you got the 5,000, what does that mean?
You lost
You lost the painting, but it also means you had the insurance. And the insurance cost you something. So it's $4,750. So it's your 5,000 from the insurance return, 5,000 minus 250. This is your premium. You still have to pay your premium. Okay, well, that equals negative 250 times 0.99 plus 4750 times 0.01, and survey says negative 250 times 0.99 plus 4750 times 0.01 equals minus 200. So your expected return on the insurance policy is minus 200. Now you might say, oh, that seems like a bad deal. Well, maybe, maybe not. It depends. If you had a large number of paintings, aggregate, probably it's not a great deal. But you have to keep in mind, and this is a colleague I was talking to him about this the other night. And he said, well, think of it like house insurance. You insure your house. The insurance company is going to make money off of you in the long run. So the expected value of what you get from your insurance on your house will be negative. But here's the thing. If you lose the house, okay, the insurance company has to pay $400,000 or whatever the house is worth. If you didn't have the insurance, for all intents and purposes, it's like infinity that you have to pay. Because that's a lot of money. So you're basically hedging your bets to say, look, I don't want to have to be stuck because I probably couldn't recover.